Let us discuss the operations on binomial heap data structure. The first operation is make the binomial heap. Here this function returns an object h. H is nothing but the binomial heap. It will create an object of type h, then make its head field null. These activities can be done in a constant time, so its time complexity is big O1. The next operation is finding the minimum element in the given binomial heap. Binomial heap minimum, we know this binomial trees follow the minimum heap property. So the minimum element will be at the root of every tree. So we have to traverse the roots and find out the root with minimum key value. That is our task. For that, first we will check whether it is whether this h is null or not. If it is null, no binomial heap, we can exit. Otherwise, we will be making a pointer x pointing the first node through head dot h. Remember, h is an object; it has a field head which will be pointing the first node. Okay, so x also points to the first node. Then we will maintain a variable min to hold the minimum value. So this will be assigned the key field of x. This is a node pointed by x. Its key field is 10. Then minimum node, another pointer, min node, which will maintain a link to the node containing minimum value. Okay, so it will be 10 now. Remember, this represents node and this represents value. And here we are keeping min equal to key of x. Okay, so we follow CLRS notations. X min equal to key of x, then minimum node equal to x. Then x will be advanced, x will become the next node. Then we will check whether this x equal to null or not. The binomial heap is over or not. Okay, it is not over, x not equal to null. Then we will compare the key field of x. X presents at present x points this node, its key value is 7. So 7 is less than present minimum is 10. Okay, this condition is correct. So we will be updating minimum value as well as the minimum node. Okay, so it is key of x, it is 7, and the node is this one. This is the minimum. Then x will be advanced, x equal to sibling of x. Yes, x will be sibling of x. Then again inside the while loop, x not equal to null, the condition is correct. If we will check key of x, that is 12. 12 is less than the present minimum. Present minimum is 7. The condition is wrong, so we will not be updating the minimum value as well as the minimum node. Okay. Again, x will be advanced, x equal to sibling of x. Remember, we are following the CLRS notations. X is null now. The binomial heap is over. There is no more binomial tree there. Okay. Then we are out of this while loop. We will be returning the minimum node. So this one will be returned. This node carries the minimum value. Remember, this is the structure of this node: parent, key, degree, link to left child and link to right sibling. The next question is, what is the time complexity of this algorithm? Here we have to traverse all the rows of all binomial trees. The question is, how many binomial tree will be there in this binomial heap? That is the question. Its answer is, if there are n nodes, the number of binomial trees are at most the maximum is lower bound log n is the number of nodes, lower bound log n plus 1. This is the at most, this is the maximum number of binomial trees you can expect. So the complexity will be big O log n, that is we will be traversing all the routes. There will be log n, lower bound log n plus 1 binomial trees. So you can expect that much binomial trees maximum. So its complexity will be big O log n. And remember, the minimum values are appearing in these rows because every binomial tree maintain the minimum heap property.